Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to continue looking at the matrix equation. So here's where we left. We left off with this interesting idea. We left off with this problem of 3 times x equals 6. And if you want to just get to the answer, which is 2, get that off of your shoulders. But the 2 isn't what's important here. What's important is this. When you solve this, if you were to write it out carefully, you would say that you would take 1/3 times 3x, and you would take 1/3 times 6. Okay? Now, we can write this 1/3 as 3 to the minus 1 times 3 times x. And again, the 1/3 is 3 to the minus 1 times 6. Now, look at what happens right here. When you take a number and you multiply it by its inverse, you get what's called the multiplicative identity, which we know this is 1. And I'm going to leave this as it is. So, and then for simplicity, we usually don't even write the 1. We would just write it as x equals the multiplicative inverse times some number. So the question that we came up with here was, well, what if all of these were not just numbers in a simple variable? What if these were what if this is a matrix, a vector, and a vector? In other words, if I have this, the matrix equation, ax equals b, and if I have, do I have an A inverse that I can multiply both sides by? Such that this, the inverse of A, would give me an identity. And if I multiply the identity by that vector, it's exactly what you would expect. It's just the vector x. Okay, so that's the question today is this true? Is this correct? Actually, before I even make that statement, there's one more statement that needs to go along with this, and that is also, let's come back to our simple numbers. If this problem was changed ever so slightly, maybe it's 3 times x equals 0. Well, it doesn't take any effort to solve that. There's only one answer, and that is that x has to be 0. And we utilize this property in solving quadratics. So the question here then also has to be asked. If you have a matrix times a vector equals 0, and now I'm going to put, does that imply, that's what this arrow is, question mark. Does that imply that x equals 0? Remember, this is the vector x. This is just a number x. So maybe I should write it this way. Maybe that would look older. That's the question, and we're going to see what the answer is to that. So let's try this. The matrix that we were working with was A equals, or I'll just write it. Yeah, we'll write A. So A was the matrix, or is the matrix 1, minus 1, 0. 0, 1, minus 1, 0, 0, 1. And we want to solve this problem. A, x equals b. And what we want is solve for x. Solve for x. Okay, let's do that. So I'm going to write this out. This is 1 minus 1, 0, 0, 1, minus 1, 0, 0, 1, times x. Well, remember, x is x1, it's x2, it's x3, and this is going to equal the vector of b. Let's write it as its elements, b1, b2, and b3. Okay, so this is in our previous session. What we did is we said, well, we can take the row dotted with the vector, and that would give me the first element in B. And the second row dotted with the vector would give me my second element of B. And third row dotted with the vector x would give me my third element of B. So let's write these out. What this tells me then is it says that 1 times x1 plus 0 plus 0. So in other words, this says that x1, I'll write it this way. We'll just write it once out in matrix notation, and then we'll solve this. This says that x1, I'm going to write my new vector like that, is equal to b1. Okay, and I'm going to put my b's down here, b2, b3. Okay, now if we multiply again, we have a minus x1 plus an x2 and a 0. Okay, and then our third component is going to be a 0 minus an x2 plus an x3. Well, look at this. The first row is very simple. x1 is b1. So let's come over here a little bit and solve that. I'm going to write these down. This says that x1 is equal to b1. Now the next one says minus x1 plus x2 is b2. Okay. Well, let's write it this way. This says then that x2 is x1 plus b2. But look at this. We already know what x1 is. It's b1, so x2 is very simply b1 plus b2. And let's look at our third equation here. This is the first element. Here's our second. And then let's take a look for our third element is going to be minus x2. Oops, that's a funny looking x2. Minus x2 plus x3 is equal to b3. I should have little tails on those. There. Well, let's solve for x3. This says then that x3 is equal to x2 plus b3. But look at this. x2, well, we just figured out that that is b1 plus b2. So in other words, x3 is b1 plus b2 plus b3. Okay. Wait a minute, we're done. We solved it. Let's come over here and let's write our answer that we've just uncovered. Notice this, the vector x is x1, x2, x3. And this is equal to, well, what did we just discover? It's equal to b1. It's equal to b1 plus b2. I'm just writing this. There's my x2. And my x3 is b1 plus b2 plus b3. Now you have to look closely. You have to remember, look at what this is. These are components being added. Like, for example, what if I put up here a 0 B2 and maybe a 0 B3? And maybe I could put in a 0 B3 here. In other words, let's remember that this is a linear combination here with a coefficient of B1. This is B1 times the vector of 1, 1, 1. Plus, look at this, we have this common multiple of B2. And it's times 0, 1, 1. 0, 1, 1. Plus, notice that I have this common multiple now of B3. B3, that's the scalar. That's the scalar, B3. We have 0, 0, 1. Oh, but look at this. If you remember, this is a linear combination. The column vectors become the columns of the matrix. The coefficients become the vector. So this is 1, 1, 1, 0, 1, 1, 0, 0, 1. There's my column vectors as columns of the matrix times the vector of coefficients B1, B2, B3. Now, what did we just find? Let me take you back here. What did we just do? We just found X equals A inverse B. We found A inverse. Let me come back. That's what this is. This is the vector X written as A inverse times B. And we're not going to do this, but I suspect that if you take this A inverse and you multiply it by the matrix of A, you should get the identity matrix, and we'll discover that soon enough. Okay, now there's one more thing that I said over here. There's this odd question. It says that if A times X equals 0, does that imply that X equals 0? So in this problem here, if I was to put zeros right there, well, then this would be 0 of this first vector plus 0 of the second vector plus 0 of the third vector. And so, yes, indeed, A times X with X would be, if B is 0, then the vector X would also be 0. Okay? So, that seems easy enough, doesn't it? What if I make a subtle change? Here's my change. I'm going to call this the matrix C. So what is C? C is 1. No, let's call it A with a star. Meaning it's very close to A, but we just messed with it just a little. How are we going to do that? Let's write 1 minus 1, 0. 0, 1, minus 1. And then let's bring this minus 1 back up instead of dropping it off. Okay? And let's do the same thing. So the problem starts out with A star times the vector of X equals B. And again, solve for X. Let's follow this exact same process. And I would actually encourage you at this point to stop the video. Try it on your own. So please take a moment, stop the video, and go through this process and see if you can discover A inverse on your own. Okay? Then come back here and we'll see what you've discovered. All right, let's do this. So if I set the problem up in the same fashion, we'll go a little faster now. I have 1 minus 1, 0, 0, 1, minus 1, minus 1, 0, 1, times the vector x1, x2, x3, b1, b2, b3. So I'm going to go straight to my equations. Here's my first equation. My first equation says that 1x1 minus an x3 is b1. Okay. Let's solve that. Let's say, in other words, that x1 is b1 plus x3. Not sure if that helps us. 2. The second element is going to be a minus x1 plus an x2. And that's going to be b2. So what this is going to give me is that x2 is x1 plus b2. Okay, and then my third element of x is going to be minus an x2 plus an x3. Minus x2 plus x3 is b3. Let's write that. So x3 is x2 plus b3. Oh, but look at this. Well, x2 is x1 right up here plus b2 plus b3. Oh, and there's x1. Look at that. x1 is right there. So this is, and I'm going to write that x3 again. This is x3 is equal to b1 plus x3 plus b2 plus b3. Are you coming up with this as well? What happens? Well, those cancel. This really is it's this equation that 0 is b1 plus b2 plus b3. What just happened? What just happened is, notice the x's were all removed. So this seems like nonsense, and what it's telling us is very simply this. This is math, the algebra's way of communicating to us that, in fact, this problem can't be solved. There is no solution. So what does that mean? So look, there's no solution. i.e., we call it A star inverse does not exist. There's one more thing. That was our second question that we asked is, well, what about this? What about A star x and the 0 vector? What about that then? Let me write that down. Let me write that. Well, if A times x, this is minus 1. Oops, sorry. Just writing down A star is 1, minus 1, 0. It's 0, 1, minus 1. It's minus 1, 0, 1 times the vector of x x1, x2, and x3. And this has to equal the 0 vector, which is the vector of which each component or each element is 0. Well, what is this? This means this is a linear combination. This says that if you take a scalar, x1, times the first vector, that's 1, minus 1, 0, plus the second weight, or scalar, x2, times 0, 1, minus 1, plus x3 times this third column vector, minus 1, 0, 1. Is there some linear combination that would give me 0, 0, 0? Okay, watch this. Watch this. If x1 is 0, x2 is 0, and x3 is 0, this would be 0 plus 0 plus 0. That would be 0. And you might say, oh, well, that's satisfying, right? Because x equals 0 does work. But look closer. Look closer. What if this was a 1? And what if, I'm sorry, not this. If x1 is 1? What if x2 is 1? What if x3 is a 1? What if I just wrote it this way? That means 1 plus 0 minus 1. Well, 1 minus 1 is 0. Minus 1 plus 1 is also 0. And minus 1 plus 1 is 0. Wait a minute. What did we just discover? We just discovered that when x is 1, 1, 1, when x is 1, 1, 1, then a star times x still equals 0, but that's not 0. That flies in the face of the property that we've used so many times to solve so many problems. And it's this conundrum, and it's the finding of the inverse that we will be spending many, many more lectures together on. Thanks for watching.